In this lesson, we'll be looking at angles in a Cartesian plane, and we're going to be focusing on using radians. In order to do that, we need to remind ourselves about special triangles and the special angles. So if you'll recall from grade 11, here are the special angles that you would have been familiar with, the 45 degree, the 30 degree, and the 60. And we need to memorize the lengths of these sides. Remember, if you had math with me, that this is a 1, 1. I call this a 1, 1, 2, but it's a square root of 2. And I call this one the 1, 2, 3, but it's the square root of 3. So these are the sides of these triangles, and these are the exact values. Keep in mind that when you're trying to remember these, that first of all, this triangle has 45s in both of these angles. It makes it an isosceles triangle, so both of these sides are 1, and the square root of 2 is larger than 1, and the hypotenuse always is the largest side. Similarly over here, 1 is opposite the smallest angle because it's the smallest side length, and so they should go together. They have to go together. And then the root of 3, if you calculate that on your calculator, is in between 1 and 2. So 2 is the largest value. It goes on the hypotenuse. Now I'd like you to go ahead and practice writing the trigonometric ratios for each of these angles. So sine, cos, and tan, just the primary ones. The sine of 45 degrees is equal to the opposite over the hypotenuse. So that's 1 over root 2. The cos of 45 degrees is equal to the adjacent over the hypotenuse, which in this case is also 1 over root 2. And the tan of 45, which is the opposite over the adjacent, is equal to 1 over 1. So we get 1 over 1, or just 1. And keep in mind this an acronym SOHCAHTOA. Sine is the opposite over the hypotenuse, cos is the adjacent over the hypotenuse, and tan is the opposite over the adjacent. So now coming over to this triangle, we're going to do sine, cos, and tan of 30 and then of 60. The sine of 30 is equal to the opposite over the hypotenuse, that's 1 over 2. The cos of 30 is equal to the adjacent over the hypotenuse, which is root 3 over 2. And the tan of 30 is equal to the opposite over the adjacent, which is 1 over the root of 3. Going on now to the 60, which is over here. And you may be familiar with the fact that by switching to this other angle now, the two ratios, sine and cos, are going to switch because of these sides switching places in terms of which is the adjacent and which is the opposite. The sine of 60 degrees is equal to the opposite over the hypotenuse. The cos of 60 degrees is equal to the adjacent, which is 1 over the hypotenuse, and the tan of 60 degrees is equal to the opposite over the adjacent, so that's root 3 over 1, or simply root 3. Now, something I did not mention yet is the fact that we prefer not to have numbers that are not integers or whole numbers whole numbers in the denominator of a fraction, because fractions are always out of a whole, and so the square root of 2 is really a decimal value if we evaluated it. So we call this rationalizing the denominator. We would multiply this by root 2, and then multiply the numerator by root 2 so we can get an equivalent fraction. And so what we end up with is root 2 over 2. Now, if you're using 1 over root 2 as an intermediary step, that's fine. But whenever you leave it as a final value, then you want to rationalize it in this way so it's actually out of a whole. And so we would do the same with each of these. I'm not going to rewrite the multiplying each time. So if we multiply by root 2 here, we again end up with root 2 over 2. In this case, we would multiply numerator and denominator by root 3. So that would give us root 3 in the numerator. And then when you multiply a root by itself, you're basically undoing it, because the definition is the square root of a number multiplied by itself gives you that number. And that number in this case is 3, if we multiply that by square root of 3. And so now we've rationalized all of our ratios. Now, that's going back to grade 11 when you did this in degrees. Now what I want you to do is take these same triangles and duplicate what we just did up above in radians. And as in the past, I would suggest that you stop right now with the video and go ahead and see if you can fill these in on your own. So what you want to do is the same triangles as above, only the angles will be in radians. And we learned the last lesson how to convert from degrees to radians. And so you can convert those degrees up above to radians, or you may already be getting to the point where you know what they're equal to in terms of radians. So this 45-45 triangle is pi by 4 in radians. And still the 1, 1, 2, where this is the square root of 2. And then in terms of radians over here, 30 is the same as pi by 6. And 60 is the same as pi by 3. And this is the 1, 2, 3. 1, 2, 3. And this is square root. Writing out the ratios in radians, the sine of pi by 4 is equal to, and we don't need to take as much time on these because we just did them up above, so opposite over hypotenuse, 1 over root 2, or that's equal to root 2 over 2. The cos of pi by 4 is equal to the adjacent over the hypotenuse, which is 1 over root 2, and rationalized, that would be root 2 over 2. And the tan of 45, or the tan of pi by 4 in this case, is equal to the opposite over the adjacent, which is 1 over 1, which is just 1. Coming over to this triangle, starting with pi by 6, the sine of pi by 6 is equal to the opposite over the hypotenuse, which is 1/2. The cos of pi by 6 is equal to the adjacent over the hypotenuse, which is root 3 over 2. And the tan of pi by 6 is equal to the opposite over the adjacent, which is 1 over root 3. And that gives us root 3 over 3 if we rationalize it. And finally, looking at pi by 3, the sine of pi by 3 is equal to the opposite over the hypotenuse, which is root 3 over 2. The cos of pi by 3 is equal to the adjacent over the hypotenuse, which is 1 over 2, or 1/2. And then tan of pi by 3 is equal to the opposite over the adjacent, which is root 3 over 1, or simply root 3. And so as I mentioned, you'll notice that when we switch to between these two angles, that now these ratio values have switched places because the sides have switched places. So now what we have is the special triangles and their ratios, or special angles, and their ratios in terms of radians. Now what we have is these special angles for these triangles in terms of radian measure. Now what we have here is the ratios for the special angles given in terms of radians. Right here are some facts that are from grade 11. So I need you to take a moment and recall these. The angle or the terminal arm rotates in a counterclockwise direction. And then for negative angles, it rotates in the opposite direction. This is called the terminal arm. It's also called the radial arm because it could be forming the radius of a circle if we draw a circle using the end of that arm. And then there's the cast rule that helps us to know which ratios are positive, and they're listed here. We have that all the ratios are positive, the sine ratios are positive, tan is positive, and the cosine of ratios is positive in the C quadrant. Now, this is written in terms of starting with the all quadrant, which is the first quadrant. So this is quadrants 1, 2, 3, and 4. When we talk about the rule, though, we refer to it as the cast rule. And so over here, then, it simply depicts some of the relationships between the angle, theta, which is the standard angle, and its related acute. Typically, we will use beta for this. Here, they've used a subscript instead, but they're showing you the relationship in terms of get theta between the given angles that exist and the related acute angle. So in this case, this angle would be 180 degrees plus the angle beta. And in terms of radians, this would be pi plus theta, or what we would call beta here. Let's go down to example 1. In all of these examples now, we are going to be working in radians. So remember to put your calculator in radian mode. There are 3 modes: degree, radians, and gradians. So you want to make sure that you use the DRG button or go to your mode button or setup and make sure that you have it in degrees, radians, or we don't typically use gradians. So in this case, you want to make sure you're in radians. We're being asked here to label the sides of the triangle first. So based on this point, this is X and Y. So this length here is 7, and this side length is minus 7. The adjacent and the opposite. And then this R here is not known, but we can use Pythagorean's theorem in order to find it. So R squared is equal to 7 squared plus 7 squared. R squared is equal to 49 plus 49, that's 98. So R squared, R is equal to the square root of 98. Remember that when you do a square root, we need to make sure that we've simplified it. So you're looking for the highest possible square root that is a multiple of this number. And in this case, we have a clue up here because we have two 49s. 49 is a perfect square, and 49 times 2 is 98. So this is equal to the square root of 49 times 2. And so r is equal to 7. Square root of 49 is 7, root 2. Now we can label this side then. This is equal to 7 root 2. The next step is for us to find what the three primary trig ratios are. We found the length of the terminal arm. So the three trig ratios are what we just were doing for the special angles. Starting with sine, and the primary angle is theta. So the sine of theta, but this triangle, if you think back to grade 11, remember that in order to do these angles that are bigger than 90, we are taking acute triangles and putting them in all the quadrants. So in this case, this triangle here is actually the triangle for theta. And if you were to look back at trigonometry for Cartesian plane in grade 11, you would recall that the same triangle could be placed in all the quadrants, but the sides are changing in terms of their size, in terms of their signs, not their size. So beta is our reference point. For sine, it's the opposite over the hypotenuse. So sine of theta is 7 over the 7 root 2. Simplifying, that gives us 1 over root 2. And because this is a final answer, we're going to rationalize it to root 2 over 2. Now, this brings us to a point that we could have recognized this triangle, even though the values are different, that in reality, in terms of scale, this is the 1, 1, 2 triangle, which is 1, 1 root 2. We see here that 7 over minus 7 gives us minus 1, and we also have a root 2 in this hypotenuse. If we divided all these by 7, which would be a similar triangle to this one, we would have minus 1, 1, and root 2, which is really our special triangle. So we could have used that fact as well in order to answer these. Now I'm just going to go ahead and answer them according to the sides that we have. So the cos of theta is equal to the adjacent, which is minus 7, over the hypotenuse, which is 7 root 2. So that gives us minus. Rationalizing it, we have 7 root 2, because we're multiplying the numerator by root 2, and we're multiplying the denominator by root 2, so that's 7 root 2 times root 2 is simply 2. This 7 cancels with this 7, so we can further reduce this. We have minus root 2 over 2. And this is what we would expect because, as we said, this is actually a special triangle. So looking at the tan of theta, I should already know that the size of it is 1, but we see here it's 7 over minus 7, opposite over adjacent, so it's minus 1. And finally it says, use one of the ratios to find the value of theta. We're supposed to use one of the ratios to find the value of theta. So we could use any of these three. I think tan looks like the nicest one just because it has a minus 1 in there. And it's less writing for me, easier to punch in my calculator. So I'm going to punch this in, but keep in mind that we already actually know what the acute angle is. This is a special triangle. So let's go and punch that in, and you'll see that that's true. second function tan of -1. Right, so what we're doing is looking up the angle that goes with this ratio. Theta is equal to the inverse tan of -1. So that should be 45 degrees, which in radians is pi by 4. And if I put my calculator in radian mode, as I mentioned before, so I'm going to change this to radian mode right now. So you'll see there, number 2 is radians. And now I will just repeat that. So the shift inverse tan of -1 gives us a decimal number. And that's where we want to know our special triangles. Some of your calculators will actually give you an exact value. So we want to use the exact value here, so we know that beta is 45 degrees, or pi by 4. And remember the work that we did figuring out the leftover angle. So if this is pi divided into 4 parts, then what we have left over here is 3 pi by 4. So therefore, theta is equal to 3 pi by 4. So keep in mind, I didn't need to use my calculator in this one. Ideally, I would recognize that this is a special triangle because of the values that I see there, the same scale as my other triangle, the 1, 1, root 2. Going on to example 2. There are 2 triangles here. Now we're basically asked to do much of the same work here, except our job is to draw the triangle and draw the terminal arm. So first of all, it says to sketch the angle. So 3 pi by 2. Hope you're getting used to the fact that this is pi. So half of pi is this right here, which in degrees would be 90. So 3 pi by 2s would be 1, 2, 3. So it turns out that our line is right on the terminal arm. So our terminal arm is falling right on the axis, the negative y-axis. And so this is a special case that we have to be aware of. Now what I'm going to do is draw a hypothetical triangle. Normally, right, our terminal arm's out here, but think about the fact that, and I'm just going to take this arm and rotate it. Think about the fact that as I drag this arm and rotate it around this triangle, the opposite is getting larger and larger, and the adjacent's getting smaller and smaller and smaller to the point where actually my adjacent is 0. So technically, what I have here, I'm just going to draw it over here on the side. Is I have this triangle comes out from this side, and technically the hypotenuse doesn't exist, or the adjacent doesn't exist at all. I'm going to draw an adjacent here, but I'm going to label these values to get us to think about this. So we have 0 on this side. When we talk about this type of a triangle, we usually talk about the radial arm being 1. So I have a 1 here. And because technically the adjacent, the opposite and the hypotenuse are really on top of each other here, what we have is a 1 here as well. And that's why I call it a hypothetical triangle, because the reality is that this triangle can't exist because of this being a 0. It's not a triangle, it's a line. But we can still think of the fact that here's my beta, if I were to draw this over here. This is my opposite. This is my hypotenuse. And so what we have here is the opposite, which is 1, over the adjacent, which is 0. And so this is undefined because we get division by 0. So what I'm doing here is covering a couple of special cases that we want to be aware of. Looking over to this triangle, we have a cotan of 5 pi over 4. So if we go 5 pi over 4, 4 pi over 4 would take us a complete pi, and then that would be one more pi after that. So that would take us to about halfway through here. And that would be 5 pi by 4. Taking this triangle and completing it. This is my theta right here, the 5 pi by 4. This angle here, if we go 4 pi by 4, there's one more, so this triangle is pi by 4. Once again, now we need to recognize this is a special triangle. So this is my 1, 1, root 2. But because these are both on these sides, this is a minus and that's a minus. So if I want to determine the ratio value for this, cotan is the adjacent over the opposite. So the adjacent here is minus 1 and the opposite is minus 1. So minus 1 over minus 1 gives us 1. And again, that makes sense because this is a special triangle. Coming down to these two examples, we have sine of 5 pi by 3. So we're dividing pi into 3 parts. And so there would be 3 and 2 more, so that would be 2/3 in here. So if we go 2/3, that would actually take us over to this side. So a third and another third would take us somewhere over here. And so this would be 5 pi by 3, which leaves us a pi by 3 left over here. Because this would be 6 pi by 3 all the way around, or 6 divided by 3 is 2 pi. 2 pi is a full circle. So labeling our sides, this is a pi by 3 triangle. So that's our 1, 2, 3. So that makes this side root 3 over root 3. And this side would be the 1, because now this is the largest side compared to, largest angle compared to this angle, which is pi by 6. In the other triangle we had, the pi by 6 was here. So this is the root 3 because it's opposite this middle-sized angle. The 1 is opposite the pi by 6, which would now be this angle. So that makes this minus, because it's down below the x-axis. And this ratio then is the opposite over the hypotenuse, which is minus root 3 over 2. Over in this triangle, we have 5 pi by 6. we go 5 pi by 6, this would be 6 pi by 6 because we're dividing pi into 6 parts. So 5 pi by 6 would be over here with 1 pi by 6 left over. So I will have a pi by 6 left over here. And then this angle is 5 pi by 6. So once again, in this case, we have a special triangle. That's pi by 6. The opposite, so we have 1, 2, 3, where this is root 3, right? This is the 1, 2, 3 triangle. So the ratio here is the adjacent over the hypotenuse, which is root 3 over 2. However, this is on the negative side of the x-axis, so this is actually negative root 3 over 2. Now in example 3, they give us an interval as our guide in this case. And so we're being told that the terminal arm of an angle, so the rotating arm, in standard position passes through the point -5, -7, determining the measure of the angle in radians over the interval 0 to 2 pi. -7, -5 would be approximately here and down here. I don't have a scale, but I'm going to do them relative to each other, so it's going to be a little bit longer down than it is over. And this is just a sketch, so it's -5, -7. So this is my terminal line. The angle that we are interested in is this angle right here. This will be our theta. And so in order to find theta, we need to work with this acute triangle here, and we need to find out what beta is. So this opposite side here is -7, and this is -5. The opposite over the adjacent, that would be tan. The tan of theta is equal to -7, the opposite over the adjacent, -5, and that's 7 over 5. Therefore, theta, and I'm going to just get rid of that because what we have to be careful of is we don't know what kind of answer we're going to get at this point. Because of the possibility of there being an angle here and here, if you think of the cast rule, tan is positive in this quadrant, and it's also positive in this quadrant. So both of these could yield the same answer. So we're going to have to interpret our answer once we do the inverse tan. So I'm not going to say it's theta yet. I'm just going to do the inverse tan of 7 over 5 and see what angle I get. Second function, tan of 7 over 5. I'm going to make sure my calculator is in radians. So there I'm in radians, and it gives me an answer of 0.95. So that's 0.95. Now, what I need to get used to when I'm working in radians is that value there an acute value, or is it actually greater than 90, right? Because if it's greater than 90, it should be this answer I'm looking for here, but if it's less than 90, then it's the beta. So the way we think about that is to remember that this is pi by 2, which is 90. So pi by 2, if I do that on my calculator, pi divided by 2 is equal to 1.57, approximately. So 1.57, this 0.95 is less than that. So this is an acute angle. So what we can now do is label this beta as 0.95. Because this value is less than here, this is actually beta. So now I can label what it is, right? It's not theta, it's actually the beta. So now if I want to find theta, I need to take pi and add 0.95. And remember, pi is actually a number, right? It's approximately 3.14. We're using that constant because it's an exact value. We can punch it in our calculator and it goes to many decimal places, which increases accuracy, but it's still just a number. So when we do theta here, we're going to do pi plus 0.95 and put that in the calculator. Pi plus 0.95, and that gives us approximately 4.09. So that is our theta. Now the final question gives us a ratio and says find the angles in this interval. Now in the question above, we were given a point already. So this didn't have much impact on us because we were already told where the angle was. For there to be an answer at all, we really needed something that went past this angle, which in this case, if we go 0 to 2 pi, they also could give us an interval of 0 to 3 pi over 2, and that would have included this angle. Now keep in mind, thinking back to grade 11 and what you know about angles in a Cartesian plane here, that for any ratio there's always two values, either two positive values. So in case of sine, if we think about the cast rule, for sine, there are the possibilities of a positive angle here and here, so there's two. In this case, it's negative, so those are the two possible angles down here. So what we want to do is draw our lines for each of these angles. So there could be an angle here, and the opposite is going to be 1, and the hypotenuse is 2. And then there could be a possibility of an angle here. Now we want to label our sides, so the opposite. Now keep in mind that the hypotenuse is always positive in the Cartesian plane. It's a rotating arm. It's not an xy value, so it's always positive. So that means that the opposite is the negative value, and that makes sense with our diagram. And so the first thing we're going to be doing then is we're going to find what this angle is. Eventually we want beta so that we can get everything. We don't know again what we're going to get when we do the inverse sine of minus 1/2. So again, I won't write theta or beta at this point in time. I'm just going to do the inverse sine of minus 1/2. Second function, sine of minus 1/2. And that gives us minus 0.52. And you may have noticed here, now here's an example, right? And this is what we have to watch for. My calculator, in this case, my calculator, and some of yours certainly give you exact values. That's pi by 6. And see, when we look at this, what we want to get used to recognizing is, oh yeah, this is the 1, 2, 3, right? So ideally, we would recognize that at the beginning and go ahead and label this as the 1, 2, root 3, and know that we are supposed to do an exact value here. So this is the 1, that's opposite the smallest angle, which is pi by 3. So our related acute is pi by 3. So I know that this value here is pi by 3, and once again, or pardon me, that's pi by 6. And so this, once again, is our beta. Now, based on this interval, we have to do this rotation, and every time we sweep one of these angles, we have to record it. Now, this is a negative rotation, so starting on the primary, the main axis, the principal axis right here, I have to go back to minus pi over 2. That means I pass this angle, so that means I'm going minus pi by 6 to here. So theta is equal to minus pi by 6. Now rotating forward 2 pi, I pass this angle here. So when I come to this angle here, that's pi plus pi by 6, or 6 pi by 6 plus 1 more is 7 pi by 6. And the last angle, rotating around to here. So in this case, it's easier to think of the fact that if I go 2 pi, I back up pi by 6. So 6 pi by 6, 12 pi by 6, back up 1, that's 11 pi by 6. And so now you can go ahead and try practicing finding angles and ratios using radian measure and some values that are exact and some that aren't.